Hi, welcome back to our course on Explainable AI, Theory, Applications, and Research. In this lecture, let us learn about counterfactual explanations. We will learn what exactly it is and how to even implement that. So I personally find counterfactual explanations very fascinating because it's useful. You can tell someone these are the changes that you should make to bring a change in the outcome. So if an ML model is predicting that someone has diabetes, you can tell using counterfactual explanations what is the change that they can make to flip the prediction probability. So let's see how to do this. So imagine we have the data of a patient who has certain amount of glucose, BMI. I'm not showing the units here. It's not relevant, but imagine they are standard units: glucose, BMI, body mass index 22, exercise duration per week 19 minutes. And let's say the original data says that this person is diabetic. This person is not diabetic. An example of what is a counterfactual explanation is as following. Imagine that the same person, if their glucose level increases from 175 to 195, then this person becomes diabetic, like this becomes true. This is an example of counterfactual explanation. Here is another example. Instead of changing glucose or BMI, if the exercise duration reduces from 19 minutes per week to 5 minutes per week, let's say if this person's diabetic status becomes from false to true, that is another example. Or you can also just have an increase in BMI, and if the same change happens. These are all examples of counterfactual explanations. Now, these counterfactual explanations make sense only in presence of a model that can make this prediction, whether based on set of values of features, whether the prediction is false or true or anything else. So the definition of counterfactual explanations is that it is the smallest amount of change we can bring in a feature or even in a set of features that changes the prediction to another output. So if it's a binary prediction, if we change the value of one feature, whether we increase or decrease it, if that will change the output value, that is an example of a counterfactual explanation. And this is extremely important and useful in an example like this. If there is a person called Diana, and imagine this is her set of features: glucose, BMI, exercise duration, and calories. And there is a machine learning model which is trained on a lot of data sets like this. So not only on Diana's personal data sets, but also the data set of many other people. And let's say this black box complex machine learning model makes a prediction that with 90% probability, Diana has diabetes. So essentially the model is saying, if it was a binary classification, the model is essentially saying Diana is diabetic. Now so this is the prediction of the model. Now the interesting question is, what is Diana really interested in is, what can I change in my routine or lifestyle, or among the list of my features, what can I change so that I can reduce my probability of having diabetes? So imagine that she did something like this. So her glucose level remains the same as now, BMI, exercise duration, all of those things remain, but she reduces her calories from 2000 to 1500 per day. And as a result of this, imagine that the probability for diabetes goes from 90% to 43%. That is almost like going from having a prediction that this person is diabetic to this person is not diabetic. Now, don't worry if this data set itself is not making sense. I mean, I don't know if a person with 195 glucose is actually diabetic or not, because I made up these numbers. But the idea here is, what is the smallest amount of change that Diana can make in her life so that she can go from being diabetic to being not diabetic? So this is an example of counterfactual explanation in this case. So here the feature that we have changed, the only feature that we have changed in fact is the calories. Calories have been decreased. It may also happen that if she had increased the exercise duration, or maybe kept the BMI the same but reduced the glucose level, glucose level, all of those might have also helped in her going from being diabetic to being not diabetic, and these are all counterfactual explanations. So if we can generate counterfactual explanations for any given data point. So let's say I have a model that is trained on a lot of data, and I make a prediction on a person like Diana saying that she is diabetic. And now if I can generate a list of counterfactual explanations like this, then I can actually provide recommendations to Diana based on my model that, okay, you have several different options. Either you exercise for 27 minutes, or you decrease your calorie intake, or maybe you optimize your BMI from 22 to maybe something else, or you use something or do something to reduce the blood glucose level. So you can give Diana different suggestions based on the counterfactual explanation. So this is where the ML model is actually becoming helpful, right? Because it's not just helpful. I mean, it is great if the model can predict her diabetes probability depending on her parameters, her feature values. But what is even more useful is to tell her actionable items. So things that she can take decisions upon. So that is the utility of counterfactual explanations. So it answers the question, what is the smallest change that Diana can make to change her or flip her diabetic prediction? Now, with that understanding, that's all. I mean, about counterfactual explanations, that's all what you need to know. But let's see how to implement this in code. So we'll be coding in Google Colab, and of course, I'll be sharing the Colab notebook link with you. But before going into that, let us look at what data set we'll be considering. So in this particular lecture today, for example, we'll be using a data set called a stroke prediction dataset from Kaggle. So I have downloaded a CSV file from Kaggle, and I'll be using that. And I will share the link to this Kaggle notebook, to this dataset link, where you can click this download button to download the CSV file. I'll share the link in the description. And the model that we'll be using will be a random forest classifier. So random forest is a collection of decision trees. Each decision tree will make a prediction, and then we'll be kind of taking a sort of like a weighted average of these different predictions to generate the final result. So that is what we'll be using. And here is the workflow that we will adopt today. First, we will load the stroke dataset from the CSV file, which we will be downloading from the Kaggle. Then we'll train the random forest model. Then we'll load something called as DICE. DICE is the library which generates diverse counterfactual explanations. And then let us analyze the features that this person or whomever we are picking as the data point, that instance, let us analyze the features within that instance that can be changed to flip the prediction of the model. So this is our workflow. So with that, let's go into Google Colab and let's code this. So this is the Google Colab notebook. I have already coded up most of it, and I have tried running it. It's working nicely. So I'll walk you through it block by block. So first we'll be installing the libraries, and then we'll be importing them, and let's proceed further. So let's first install Torch. So from PyTorch, we'll be using the data loader, and then we'll also use this DICE ML. So DICE is the diverse counterfactual explanation generator. So let's install that library as well. And after this, we are importing a few different libraries. There is data loader, random forest classifier from scikit-learn, F1 score, accuracy score. Then there is, I think we are already importing this. Then we have train test split, and of course we are also using pandas. And yeah. And SMOT helps in, in the cases of an imbalanced data set, SMOT can help. So the after installing the libraries, let us import them. The installation is almost finished. It should not take too much time. And then what we do is we load the data set. So the data set that we are using will be from the CSV file that we downloaded. So what I'll do is I'll load the data set over here. Maybe I can right click So click on this folder icon. So this is a temporary folder. So when the runtime of this notebook gets disconnected, you will lose the folder, but that's okay. So right click here, new folder. I'll rename it as data, and into this I can upload. So right click on the three dots and then stroke data, upload. So this is okay, and healthcare data set should be uploaded here. So that is here. Now hopefully if the installation has finished, I think it's almost getting finished. Then right click here, click the three dots and then click copy path, and this path is, I'll just paste the path here for you to see. So this is the path, right? So this is what we'll be using. We don't need this piece of code. I'll just comment this. So now we'll load the data. So we have this custom data loader function, which will load the data set, pre-process. It can do the splitting, etc. So firstly, let me paste the data path here. So this is the path to the CSV file, and then I can run this code. Okay, so the data has been loaded, and then what we do is from the data, using the data loader, the data is split into the train values, test values, train labels, and test labels. So let us run that. Okay, so here what we are printing is the shape of the training dataset and test dataset. So there are 22 columns in the training data and in the test data, and in the training data there are 7,500, around 7,500 data points, and test data has around 982 data points. So I guess the train test split is something like 982 divided by 7542 plus 982 multiplied by 100. So this is the percentage. So around 11 to 12% is used for testing, and remaining is used for training. We can also print this training data just to see how it looks like. So print xtrain, just to see how the data set looks like, all these 22 columns. So here you can see that these are the data points. So there is ID, I guess this is some kind of patient ID instead of showing the name to preserve the identity, age, presence or absence of hypertension, heart disease, average blood glucose level, BMI, gender representing male or female, or other non-binary, status of marriage, whether they have worked or whether they work in private, self-employed, children, residential type, whether they live in rural or urban places, smoking status unknown or known, then former smoker, etc. So these are all the 22 columns. We'll see this in detail, but this is just to show you how the data looks like. Now what we do is we define the random forest classifier, and we fit the training data and training labels. So the Y train should look like a series of true or false. So we can also print that. This should be like either zeros or ones or true or false. Yeah, so it's mostly 0, 1. So I guess 0 means no stroke and 1 means with stroke. So my guess is that people with if I were to print, let me print xtrain of 0. This must be this must be a no stroke person, so maybe a relatively young person. Xtrain, what's the issue here? I guess I have to do this, maybe. I'm not sure. Yeah. So this person's age is 40, and let me also print xtrain of, let's say, 6,000. So this is the person with index 6,000. Their age is 62. So, and if I also print the label x label, sorry, y train of this, I guess I just need 0 probably. Yeah, so that is 0. So 0 means no stroke, whereas if I print y train of 6000, this might be 1. I mean, it is 1, I think, most likely. Yeah, it is 1. So okay, so this is how the data set is. The first half of the data set, I guess, is all people without stroke, and the other set is with stroke. Now we are fitting random forest classifier, the X train and Y train values, and we are making predictions on the test values. And the predicted output is stored in this Y predicted, and the F1 score and accuracy is calculated using these two these two functions, which are taken from the library. So if you remember, we had imported the libraries from scikit-learn, F1 score and accuracy score. So that is what is being used here. And now we can see how accurate this random forest classifier is on this data set. So F1 score 0.5, accuracy 94%, quite good, in fact. Okay, so with this model, now let us go to the creation of counterfactual explanations. So in this video or lecture, I don't intend to teach you details about the random forest classifier, because that's not the intention of this lecture. My intention is to show you, if we have a trained random forest classifier or any trained ML model, how can we generate counterfactual explanations? So that is my goal. So we are importing dice ML. I think we already imported this somewhere here. I guess we did not. We just installed it. We just pip installed dice ML. We did not import it. Okay, so we'll import it, and then we will define the data set. So once I run this, you will see how this looks like, the counterfactual explanations. And let me also create the data and model objects and generate visualization. Okay, so firstly, let me not show this. Let me just show this. So what we are doing here is, we selected a particular instance from the data point. So the instance was the first data point in the test data set. And before that, here we are defining the random forest dice model, which is we pass the random forest model here, and we set scikit-learn as the backend, and the explainer, which is the explainable AI explainer in this case, which is dice, and into that we pass this RF dice. And then you can also see that the input data point for which we have to generate the counterfactual explanation is defined here as the first data point within the test data. And you can see that and this you will see even when we print. So when we print X, so if I just print this, you will see that this is the person. So essentially the ID 53802, that's the name of the person, the ID of the patient. And so this is the original instance. So ID is this, age is 80, hypertension, heart disease, etc., etc. Now what we are doing is, we are creating 3 counterfactuals, and when we print them, so here we are printing, actually let me put this. So we are printing those features which had changes. So in these 3 counterfactuals, these 3 are all the same person. So ID has not changed, which is why, so here I'm only showing the changes. So since the only show changes is true, ID has not changed, so that's why ID for these 3 instances which are generated as counterfactual explanations are the same. Age has not changed, hypertension has not changed. What is changed for the first counterfactual explanation is smoking status went from 1. I guess 1 means smoking status is this person is a smoker, I guess, or probably this person is a non-smoker, and here the smoking status is changed to 0. So so this person's smoking status, meaning this person may be a smoker, and then the stroke probability this person's prediction becomes yes, stroke positive, or this person is predicted to may have stroke. We can also display all of the values. So here, although we created 3 counterfactuals, you can see that they are all the same, probably because there are no other data points that can be changed to create this counterfactual explanation. Now let me maybe do this with another data set. So X test of 10th data point, and we can visualize this. Sometimes the counterfactual generation does not work. That's also there. So here, this person originally has no stroke, and in the counterfactual explanation, all the 3 instances have stroke. And that the reason why all these 3 instances that were created, all these 3 counterfactual explanations that were created had stroke is because the desired class is opposite of what is originally predicted. So in the original test data set, the prediction is this person has no stroke, but here this person has stroke. And what's the reason for that? To see that easily, maybe I can just print the values which changed, the feature values which has changed. So in the first example, work type self-employed. So here it was work type self-employed was 1. Probably that means this person was self-employed. Now this became 0, meaning this person is not self-employed. Then stroke probability, or I think it's the opposite, right? So work type self-employed means this person. So now if the work type becomes from self-employed to 0, maybe that means this person has no work. It's not very clear, this 1 to 0 transition, but basically it changes the prediction. It changes from 0 to 1, the stroke prediction. The second example, I would say, is even more easy to understand. So this person's smoking status was 0, meaning not a smoker, but it changed to 1. Of course, this person became a stroke probable person. Then the third example, the change is resident. Okay, in the second example, the residence type has also changed. So urban, this was an urban resident, I guess, that has become 0. So non-urban resident. In the third example, the person just became non-urban resident, and that's it. And the person's status became the person with stroke. Now, this is very interesting, right? We can also do the same thing to define a range of features. We can provide what features to vary. So here we are not constraining what features to vary. We are allowing whatever feature we are allowing whatever feature the DICE model wants to vary to be varied. But this is not very helpful, because imagine you are going to now recommend this person, okay, hey, you don't have, let's say the person originally did not have stroke, or originally had stroke. Let me find a test data set like this. Maybe one of the later test data sets might be the one with stroke. I just want to show you the importance of constraining the features. So just have a look at this. Input data point. Okay. So here, first we are defining which features you can vary: average glucose level, BMI, smoking status. The reason why this is important is because we can only give so many recommendations to people. If they are living in a rural environment, we cannot tell them, oh, you move from rural to urban environment and then your stroke probability can reduce, something like that. I'm just giving an example. So there are only certain type of explanations that makes sense or that actually helps people. So if this person's stroke level prediction was high, to reduce it, we can tell them, okay, you may reduce your glucose level, you may reduce your BMI, you may reduce, or you may become a non-smoker. So by how much should this person reduce the BMI, or by how much should they reduce the average glucose level? That is what we can give. So let us try to generate that. So here we are taking a sample data point, this person ID 50136, and the prediction is that we can try to print the prediction. Let me do that. We can print the predictions like this. Print y test of I. It should be, okay, it is 0. So one thing I noticed in the dataset is that there is somewhat imbalance. So if we try to print y test itself, which are the labels of the test dataset, you will see that most of the values are 0, meaning most of the data points are corresponding to no stroke. So there are 981 data points here, but we can print how many of these are 982 are there. We can print how many of those are zeros and how many of those are ones. Let's just see that. So here I just printed the length of the number of indices whose values are 1. Out of 982, only 53 have stroke. Remaining ones are without stroke. So that is like less than 10%, like close to 5%. So there is that issue in the data set. So although our model accuracy is like 93-94%, there is a very high likelihood that the mistakes that the models are making is in those data set which have stroke. So we can actually test that. So we can print. So let's say these are the test indices. So if we print this, these are the test indices where there is stroke, right? In the test data set for all these indices, there is stroke. And we also have a predicted indices, right? So AI is already showing that. So in predicted indices, we can also print not length with stroke. Predicted indices with stroke will be pred. So yeah. So if we run this, we can see which are the indices. So in the predicted indices with stroke, only these are the ones which has stroke. So 131 is predicted to have stroke. In the test, 131 should be there. Hopefully it's not there. Okay, so this is a wrong prediction, I guess. 254 is not there. So 254 is also a wrong prediction. I'm not sure if this is because, let me just go back. So I have created that list here, 131, 254. Y predicted is actually there are a lot of mistakes. So mistakes meaning mistakes the model is making. 613, is that correct? Okay, 613 is there. So 613 is a correct prediction. 679 is not there. It's a wrong prediction. So here the model has predicted that this person has stroke, although this person does not have stroke. 704 is not there. So there are very few data points where the model is actually getting it right. 379 is also not. So only 613 is there from this list. But on the other hand, if you try to predict, so that the 94% accuracy is coming because the model is getting everything wrong, almost everything wrong in those patients with stroke, and model is getting almost everything right in those patients without stroke. I think that's why. And in the test data set, 5% of the data is with stroke, and remaining 95% is like 95% is without stroke. So those are correct. So we can test that by just changing the ones to zeros, and you will see that here the indices will align. Yeah, you see. So okay, sorry, this is not with stroke, this is without stroke, and they will align. So model is able to predict the ones without stroke really well, but with stroke it's making a lot of mistakes. So so although the accuracy is very good, the model is in fact not very good. So we may think model is very good, but now we know that model is actually making a lot of mistakes. Actually, we could have seen this easily by just plotting a confusion matrix. We can just do that. Let's just plot a confusion matrix. So here I just plotted the confusion matrix. I just copy pasted the code. It's very simple. You can see that whenever the true label is 1, which is whenever the true label is in the test data is stroke, the predicted label is 0 for 52 of them, and only for 1 of them the true label is correct. But because there is a huge amount of no stroke data, the prediction over here is fine. 922 of them are being predicted correctly, whereas there are only 7 mistakes. So here true label is 0, but predicted label is 1. So this is only 7 mistakes, but here there are 52 mistakes. So I would even say the model is not at all good in making good predictions. But having the best possible model is not our goal here. I guess the goal is to see counterfactual explanations for the model. So really, if we look at the part where we are training, I think we might be able to do a few things to make the model better. One thing for sure is to have a balanced data set. So in the training also, we might be able to see the same thing. So let's say I change this to let's say y train, and I'll actually copy paste this code. So y train equal to 0, meaning the ones with stroke, and this is y train equal to 1. Stroke train. Okay, actually this is no stroke train, and this is stroke train. Number of training with stroke, with no stroke is this. Number of training with stroke, and this is len of, just to print the length of that array. I am pretty sure the second first one is much bigger. Okay, so number of training with no stroke is 3771, and number of training with stroke is also 3771, and I know exactly why this is happening. This is because we are calling that smart thing to make the imbalanced data better. So here we are kind of oversampling, because in the initial data set in the training there are a lot of no stroke data and very little with stroke data. So we use this oversampler to make sure that the data is balanced. But even with that, I think our model is not really good. So we have a lot of synthetic data here, but the model is not really good. But that's okay. I don't really care about the accuracy of the model in this lecture, at least. We can do one thing. We can print the data points corresponding to so just have a look at this. So we are printing the one that was correct in the test case. So here if we print y test of 613, this should be 0. Sorry, yeah, this should be 1. Yeah, because this was one of the few people whose stroke was correctly predicted. So this is that one point in the in our, where is the confusion matrix, this is that point which was correct. So predicted label is 1 and true label is also 1. So predicted is stroke, true is also stroke. Now let's see if we are able to generate like a counterfactual explanation for this data point. So the data point is like this. Person has this much BMI, average glucose, etc., etc., smoking status formerly smoked, and we can run here. We have a permitted range. Maybe it's difficult to even generate the counterfactual. I don't know. Okay, this is okay. So what we have done here is we have generated counterfactuals using this piece of code. So what it does is we have permitted a range of these features. Let me delete the confusion matrix. We don't need it anymore. Let me also maybe delete this and this. So all of these are not needed. So we have a glucose, average glucose level range from 40 to 300, BMI range from 15 to 45, and smoking status also I think can flip the value. And here what is done is you can see that in both cases they have changed the average glucose level. So in one case they increase the average glucose level to 250, and somehow suddenly this person goes from having stroke to not having stroke. This is super weird. I don't know if this makes sense at all. In the other case, again, average glucose level goes to 44. I don't think this is a sensible value, but at least the glucose level, average glucose level has decreased, and the stroke probability has gone from 1 to, I mean, not probability, the stroke prediction has gone from 1 to 0. I would say this, it's easier to explain for other data points in the test data set. So let me take 200. I'm sure this is a data point without stroke. So if I print y label, y test of I, this should be 0. The value should be 0. Yeah, correct. And if we run the counterfactual explanation, okay, it's not able to generate it. Okay, fine. I'll do one thing. I'll just cut and paste this here so that I don't have to run two blocks. So let's say, how about this counterfactual? In many cases, it's very difficult to create counterfactual explanations because if you don't understand why this is happening, this is a person, this I equal to 800 is a person who does not have, I think we can print this thing also, print y test of I and label of test data. So we're just printing the label of the test data, and we can see that this person is most likely 0. The label is 0. Yeah, so the label of test data is 0, so no stroke. This person's age is 14, right? So it's literally a kid, and you cannot change the parameters of this kid, any parameter of this kid in kind of any extreme to predict that this kid of age 14 will have a stroke. So it's very, very difficult. So, and that's exactly why the model is struggling to create counterfactual explanations. But if we can find an old person, I'll just randomly change these values until I find an kind of an older person, maybe age 70 or something. Then we can, this is 42, again difficult. So for young people in general, it's very difficult to create counterfactual explanations that will make, this is again a young person, I'm pretty sure stroke counterfactuals are difficult. I hope you understand why it is difficult to find counterfactual, because first of all, we are limiting that only these 3 parameters you can change, and most of these are young people, whatever I'm randomly generating. So there was another person, 15, if I remember correctly, that was working, or no? Okay, no. How about 800? I think we have tried this 920, some random numbers. Yeah, again, for all of these, it's very, very difficult to generate counterfactuals. I just want to randomly hit a person of age. Maybe I can probably print some people whose age is, to pick a person whose age is high. I can just, here anyway, I'm randomly trying. If I don't hit a person with age being high, it's very difficult to 51. How about 2 in the test data? Okay, 66. What about 1? What about 7? Of course, there are smarter ways to do this. Let me actually print some people with higher age, and let me try with that. Okay, so I have printed some people whose age is above 70. We can just test with some of these indices, 10, maybe it's easy to create counterfactual explanations. Okay, not necessarily. Okay, how about some of these people? Okay, now finally we have hit a counterfactual explanation. Let's explain this. We'll be very happy. So this person, of course, the prediction is no stroke, although it's an older person. And for this person to have stroke, all you need to have is like average glucose level being higher. So that is what is being predicted here. Only feature that is changing here is the glucose level. And you can also increase the number of counterfactual explanations. So if you put 10 here, 10 rows I think will be created, 10 counterfactual explanations. Sometimes all 10 cannot be generated. It will only generate lesser number. And here they are just changing the average glucose level. Let me find another old person which may or may not work. The counterfactuals may not happen, because if the old person is relatively healthy, it's very difficult to generate counterfactuals within this limit. We can, of course, generate counterfactuals if we don't put the parameter. Like, for example, if I remove this, right? If I remove these two, it's easy to generate counterfactuals, because now we are not limiting these parameters anymore, and it will generate as many counterfactuals as you want, because it can take crazy values. Average glucose level is 257. The original is 125. So to make this person of age 81 who does not have stroke to have stroke, here what they're doing is first gender being female is turned off, meaning mostly gender male. Actually, we can't say that, because gender male has not changed. So it's just that gender has become 0. That's all. And it doesn't make sense. I mean, they should at least, then the gender other should be 1, but we are not putting such constraints, right? And BMI from 40 to 18. I don't know why this person should have stroke, because their BMI decreases to 18.9. I have no idea. But that is what the prediction is. So the bottom line here is, if you don't constrain the feature values, then it can create random, a little bit crazy predictions which may not make too much sense. So limit the values and then try to find out the counterfactual explanations that make sense. The ideal counterfactual explanation that you need in these kinds of cases where healthcare data set is involved is, how can a person with stroke, what kind of changes can they make to go from having stroke, which is 1, to not having stroke, which is 0, right? So I'll share this notebook with you. Just try to run this yourself, and also try to run this on other kind of data. There are so many different types of healthcare or otherwise data sets. So try with some simple binary classification and see how this goes. So that's all for today's lecture. Thank you so much. We'll see you again in the next lecture.